we've got bromate 5 ions and bromide ions reacting in acidic conditions according to the reaction there. A series of experiments was carried out at a given temperature. The results were used to determine the equation for the reaction. And we have that it is first order with respect to bromate, first order with respect to bromide, and second order with respect to those. So use the data from experiment 1 to calculate a value for the rate constant. So rearranging the rate constant, K equals R divided by, and then we've got BrO3 minus multiplied by Br minus multiplied by H plus squared. Put the values in for run 1. So 2.4 times 10 to the minus 2 divided by 0.1 times 0.2 times 0.3 squared, and that equals 13. So appropriate number of significant figures. So these are all written to 2 significant figures. I should have written that down here. So 13, and the units for this, if we cancel all of these out, gives us mole minus 3, dm plus 9, seconds minus 1. Okay, complete table 2, so we can use the rate constant for working all of these out. Or we can have a look at what is going on with the reactions. It's probably easier to use K as 13 to work all of these out. So for this one in here, so that is going to be 3.6 times 10 to the minus 2 divided by, BrO minus equals BrO3 minus equals the rate, 2.4 times 10 to the minus 2 divided by K divided by 13 times, and then 0.2 times 0.3 squared times 0.2 times 0.3 squared, and that gives me a value of 0.15. And then for number 3, so it is that times that squared, and that gives me a value of 0.27. And then the final one, so this is getting the H plus squared. So H plus squared equals the square root of, so rate is 2.7 times 10 to the minus 2 divided by 13 times 0.1 times 0.1. Let's get rid of that. And if you work that out, that gives you 0.45. So the marks, there's 1 mark for the working out here, 1 mark for the correct answer, 1 mark for the units. There's then 1 mark for each correct answer in the table over here. So that gives you those 3. And then part C, in a second experiment, so we've got a results table that's partly filled in. So what we need to do now is complete the table. I've pre-worked these out just because it's easier for me to plot a graph in advance. So minus 3.30 and 3.31 times 10 to the minus 3. We're given the Arrhenius equation and we're given R. We need to plot a graph, and we need to use that the graph and the gradient and R in order to calculate the activation energy. Now I've pre-done all of this. So key thing here is, so here's where the marks are. Let me change coloured pen here. There's 1 mark for an axis. It's a step of 2 which fits quite neatly in there. So if you've got the axis using more than half of the height of the graph paper here and it is labelled, That gets you one of the marks. There's another mark if you've plotted all of the points correctly, and there is a further mark if you've got a line of best fit going through minimum of 3 points. You then need to calculate the gradient. Remember, your triangle needs to be as high as possible. So I've got the change in y here, that's from there to here, and then I've got the change in x here, which is from here to here, so those values there. And then my working out for the gradient is this bit here, so that's my gradient working out there. So the answer here that I've got is 6667, but it allows anything in the range of minus 6,500 to minus 6,800. From there, we need to use the activation energy is equal to the gradient multiplied by the gas constant. I've got minuses in here, but of course these would cancel out into the pluses. So 1 mark for the formula there, and then 1 mark for a correct activation energy by dividing it by 1,000 to get it into kilojoules. So again, any activation energy in the range of 54 to 56.5 is allowable.